lecture, maybe the battery died or what? Always happen to your session B. Session A never happened. Maybe this is a battery maybe only good enough for 2 hours. This is like 2.5 hours now for me. So okay, so let me use pointer. You see here, you have more electrons jump over this barrier. And notice that here, this is exponential decay, right? When your barrier reduces, then you will have exponentially more electrons over this barrier. And you know the current depends on how many electrons that can move over this barrier. If you have exponentially more electrons, that means exponentially more current. That's why the current exponentially depends on the applied voltage in this positive forward bias. You can apply similar argument to the hole here. Then the hole barrier also reduces, and then you have more hole that can diffuse over. And this is also depends on the exponentially depends on the barrier height. So any questions here? So we see the split of the EFP and EFN. This is EFP, this is EFN, and we see the split of the EF due to the external voltage. And again, P side push down, so the EFP lower than EFN. Okay, so then what happens when you apply electric voltage? So again, let's first start with this bound model, with charges. So what happened here? You see the negative voltage to the P side. That means you are going to have electrons inject from this terminal to the P side. So then you will have the increase of the depletion region. This is just opposite to the forward bias case. Now the depletion width will increase. This is just opposite to the positive voltage case. And let's still look at this from the band model point of view. It's easier to understand from the band model. Now this is at equilibrium. And then we apply negative voltage. Again, this N side is grounded, it's reference. That means N side, this will not move. Okay. We apply negative voltage to the P side. Then what will happen to this band? Yeah, so the Fermi level here will split. And you use that conclusion. Positive voltage push down the band. That means negative voltage pull up the band. So that means this EFP will move up, and the EC and EV will follow. So if you apply negative 0.5 volts, then the EFP will move up by 0.5 electron volts, and also EC and EV. So then if you do that, then you will see this is a band under the reverse negative voltage here. You see EFP moved up. So that means this barrier height increase, right? Forward bias lower. Now the reverse bias, this barrier increase. So then, what will happen? Let's look at this. So this is reverse bias. Now you see this EFP is higher than EFN because we said negative voltage move up the band, the Fermi level will increase. So that means this barrier height here increase. Okay. So still you have this kind of distribution of electrons in the N-type. But now you see the barrier height increase. That means almost there's no electrons can jump over. So all the diffusion current will be reflected back. But still you have this drift current. This one will not change because you still have this electron at the edge, and then this electron will fall down. But with increase of the negative voltage, you are going to get higher barrier, but your current, negative current will not increase, it will saturate. Because here, the number of electrons available to fall down is a constant. You are going to get more electrons here. This electron density is determined by the doping of this p-type, which is minority. And then no matter how large the negative voltage is, then the reverse current will not increase. That's why you see the saturation current I0 in that IV relationship. So similarly for the hole, you can argue for the hole. So any questions here? So in the reverse bias, the diffusion current are all blocked. Only this drift current will be there, and the drift current is a saturated current. It will not change. No matter how high this is waterfall, right? No matter how high this waterfall is, the number of electrons is fixed here. So then this flow is fixed. So that's why you have saturated current towards the negative voltage. All right, so this is a summary of the chain junction, the band diagram under three conditions. When equilibrium, where you have the single flat Fermi level, and then you have this built-in potential barrier. And for the forward bias, you apply positive voltage to the p-type. Then you are going to push down the p-type Fermi level, and then the barrier height reduce. Then you have this electron diffuse over the barrier. This is a majority carrier from the N-type, but once they reach the p-type, they become the minority. For the reverse bias here, right? So then you apply negative voltage to the p side. Then you are going to move up the Fermi level for the p-type. Then the barrier height here increase. So no more diffusion current, only you have this drift. And drift is due to this minority carrier in the p-type electron. So then this is a very small current, saturated current. Hopefully with this band diagram help you understand why the IV relationship, current versus voltage, is like that for this PN junction. Any questions? All right, so let's go back to the MOSFET structure. Because in this example again, this N-type MOSFET, we said that the substrate is P-type, and then for the source and the drain, you will have N-type doping. So you will have two pin junction here from this body to the source, or from this body to the drain. You have two pin junction. And here there is a guideline for the later circuit design. If you are a circuit designer, you need to design your voltage bias of your source, drain, and the body potential. You will have this kind of constraint. That is, the body cannot be forward bias. So that means this is not allowed, this condition. Let's say, for example, the source and the drain, ground, and then you apply positive voltage to your body. That means you are going to turn on the PN junction from, let's say, the body to the source, or the body to the drain. This is not allowed in the circuit design, because that means you will have large currents, exponential currents from this body contact to the source, from this body contact to the drain, which is useless, and you are going to burn the power there. So in the practical circuit design, for the N-type MOSFET, typically the body contact and the source contact will be tied together. So always the body to the source will have 0 voltage. And then the drain contact typically is a higher positive voltage. That means if the body is 0 and the drain is some positive voltage, that means the here from the body to the drain is a reverse bias. So you have very small current there. So you don't want large currents flow in the substrate, because the only useful current in the MOSFET structure is the current from the source to the drain to the surface of the silicon. We are going to discuss that more in details later. That is the current you need from the drain to the source. You don't want the substrate here, the current flow underneath. You only want the current flow from the drain to the source directly. You don't want the current flow from here or from here. So any questions? So you have to be careful when you design your circuits. Alright, so then if you look at the energy band diagram of this N-type MOSFET along the channel direction. So that means you are looking from here, from this source, this is called channel under the gate, and then this is the drain. So if you draw a line like this, and if you want to draw the band diagram along this line, then you will get this kind of band diagram. Because the source is N-type, your channel, which is the substrate or body, is P-type, and then the drain is N-type again. So you have two pin junction back to back along that direction. And this is when the VDS is 0. That means this is equilibrium state. You have a single Fermi level. And later, when we discuss the MOSFET structure, you will see that this is again a barrier control device. So when you have the current from the drain to the source, that is because this barrier height is modulated. So then you can control how many currents or how many electrons can flow over this barrier. So that is a principle of the MOSFET. We're going to discuss in more details in the following lectures. But from today, we talk about this pin junction, right? So then that is the basis for the MOSFET structure. Any questions? All right. So then we can stop here today.